Okay, so we talked plenty about trees, and we talked a little bit about graphs. And now I want to talk about a very important connection between the two, and that's the notion of a spanning tree of a graph. So first, let me talk about this graph that I drew here. Notice I didn't actually draw any arrows on the edges. What this means by convention is this is a so-called undirected graph. And what that means is this is an undirected graph. Arrows go both ways. So if I don't draw arrows, what it means is that the arrows go both ways by convention. So for example, here, 3 points to 7, and 7 also points to 3. That's what that means. So for every edge, the two nodes at opposite ends of it point to each other. So that's an undirected graph. So it's much quicker for me to not draw the arrows and to just draw them like this for now. So we'll start by focusing on undirected graphs, and then we'll see a little later directed graphs. The arrows will show up again where we don't necessarily have both. Okay. So that's an undirected graph. Now what's a spanning tree? Well, a spanning tree is a subgraph. Is a subgraph of a graph. So a subgraph means so keep all. Let's say for now that it's some subset of vertices and edges, satisfying the following properties. So actually, first of all, it has all the nodes of the original graph. Number two, it does not contain any cycles. Or sequences. A cycle is a sequence of edges from one node to the next that ends up where it started. So we don't want any of those. And the third thing is it's fully connected. So it's into one piece. So let me try to build a spanning tree on this graph that I have in the picture here. So I'm just going to start picking some edges. So let me say I choose this one. I'll bold it. Let's say that I choose this edge. I'll bold it. Now can I choose this edge? No, because that would form a cycle. If I chose that edge, I could go 2, 4, 5, and then back to 2 again. So I don't want that edge. I guess I'll choose this one. It's as good as any. Now let me choose this edge. I guess I'll choose this edge. And I don't have any cycles. That's good. If I chose this edge, I'd be in trouble because now I have a cycle that goes 3, 4, 5, 7, 8, 6, and then back to. Oh, sorry, I said 2, 4, 5, 7, 8, 6, back to 2 again. Okay, so I can't add that edge, but I have some other options. Let me add this one. Let me add this one. Am I done? Well, not quite, because look, I have this one piece here and then I have this other piece here. So I really need to add a bridge between them. So let me add this edge here. Okay, now I've got a spanning tree. So let's check. Does it have any cycles? No, I don't see any. Is it a subgraph? Yes, I used all the nodes. And also I never used any edge that wasn't in the original graph. Is it a one piece? Yeah, it looks like it is. I can find a path from any node to any other node. That's what I mean by being connected. By the way, just as an aside, that's not a correct definition in topology. That this is where computer science and math get a little mixed up. But for our purposes, connected means that I can find a path from between any two nodes. So yeah, pick any two nodes here, I'll be able to find a path. So 0 to 4, yeah, I can go 0, 7, 8, 6, 2, 4, 5. Yep. Looks like we're good, so that's a spanning tree. Okay, so couple interesting other properties of spanning trees. So other properties. Number one, for n nodes, it has n minus 1 edges. So let's see, is that right? So I had 9 nodes total here. I started counting at 0. How many edges do I have? I got 1, 2, 3, 4, 5, 6, 7, 8. Okay, that seems correct. The way that you see that is every time you connect 2 nodes to each other. So yeah, single edge connects 2 nodes. So the first edge connects 2 nodes, and then after that I keep adding 1, 1, 1. So I only need n minus 1 of them to connect n nodes. Let's see, what other property I've written down here that I wanted to share? Yeah, so okay, so another thing to note, it's kind of related to the definition, but at this point, adding any single edge creates a cycle. So any of the edges that I add at this point will create a cycle. So if I add this edge, boom, there's a cycle. I can see between 0, 3, and 7. If I add this edge, well, there's cycles all over the place. I've got a cycle 1, 3, 7, 8, but I've also got a cycle. Oh no, I guess, is that it? Can I see any other cycles here? No. Okay. But anyway, yeah, so pick any of these edges, you'll see, okay, this one's a little more interesting. This one, I can see I have a cycle that goes 7, 4, 2, 6, 8, 7. Okay, so I don't want that. But that's an interesting property. That's going to help us to prove some things later. So I wanted to say that. Okay, the last thing is removing. So adding any single edge at this point creates a cycle. Removing any edge creates a 2 or let's see, is it always 2? Yes. Removing any edge, I think I'll just say, to keep it simple, removing any edge breaks the full connection. Okay. So if I remove any of these edges, I break, this thing is no longer connected. There are some nodes that I can't find a path between. I can't bridge a path between anymore. So any single edge that I add here, so now 1 is separated from the rest. Here 1 and 3 are separated from the rest. Here 2, 4, and 5 are separated from the rest. Okay. So those are all the things I want you to know about spanning trees. Now, let's think about an algorithm to build a spanning tree. So algorithm to build. So I'm just going to say the following. So step 1, permute the edges in some random order. Okay, step 2 is for each edge in this order, add the edge if it doesn't create a cycle. Or I should say the following. No, okay, no, 4. I'm trying to think if I want to do it for a while. I think I'll just do 4. For each edge in this order, add the edge if it doesn't create a cycle. Otherwise, skip the edge. And then I'll just say repeat step 2 until the tree is connected. Okay. And so we can see this algorithm is correct because it never creates any cycles and it repeats until the tree is connected. So it satisfies all the properties of a spanning tree. And so you can implement this using union find, because if you're going to create a cycle, what it means is, so for example, if I was going to connect 5 and 6, what it means is 5 and 6 are part of the same connected component. Yeah, let's say that I was up to this point, and I was going to connect 5 and 6. Well, 5 and 6 are part of the same connected component, so adding that edge there would create a cycle. So that's what you have to do. This translates into checking to see if the nodes are part of the same connected component. Every time you add an edge, you merge them. So you can use a disjoint set data structure like implemented with something like union find to do that. So that's what I'll have you do in the next exercise. All right, cool. So that's the diagrams to build it. The last thing I want to say is, well, this doesn't really look like any of the trees that we've drawn so far, right? Like, where's the root? Like, what are the children? Like, what's going on here? So let me just explain why this is still a tree. It's a more general kind of tree than like the binary search tree and other trees that we looked at. But what you can do is think of this as a bunch of nodes connected with spaghetti. And any of these nodes you can pick up and make it the designated root node, and everything will hang down. So let's say, for example, that I picked up 7 here. Okay, so what's going to hang down from 7? So now I've sort of made 7 the root node. So down from 7, 7 is connected to 8. So there we go, it's connected to 8. It's also connected to 0. And it's also connected to 3. Okay, so 7 connected to 0. And then connected to 3. Oops. Okay. So 0. Let me get all my numbers the right size here. 0 and 3. Okay, so 7 is connected to 8, 0 and 3. 3 is connected to 1 and nothing else. So I can make 1 a child of 3 and nothing else. So see how everything's hanging down from 7. 0 is not connected to anything. 8 is connected to 6. And nothing else. I mean, yeah, it's connected to 7, but 7 is above it. Okay. So 8 is connected to 6. 6 is connected to 2. Oops, I'm trying to get my 2 here. 2 is connected to 4. Actually, we got a nice little linked list situation going on here. We've got a whole string of nodes that are connected that only have a single child. So 2 is connected to 4, and then 4 is connected to 5. And that's it. Okay. So you can see that actually this maybe starts to look a little more like trees that you're more familiar with. The only difference is that, you know, a node can have more than 2 children, so it's not a binary tree. A node can have arbitrarily many children. But yeah, so the idea is if I think of this like a bunch of spaghetti, I pick up my 7, this whole thing is going to hang down like 7, 8, 6, 2, 4, 5. This other part's going to, the 0 is going to hang down, and then the 3 and the 1 are going to hang down there. I can turn this into a tree by picking up any of these nodes. I could make 6 the root. And then 8 would kind of hang down. So if I made 6 the root, then 8 would actually hang down maybe on the other side of 6. Let me move these over actually. Yeah, so I would say, maybe draw it like this. Then 8 would hang down from 6. So the tree would look, oops, let me just get that down there. So 8 would hang down from 6. And yeah, maybe I would probably want to move that 7 down too, because 7 hangs down from 8. So anyway, I just wanted to show you there are many, many ways to draw this. I can pick up any node and turn it into a tree. So I just want to show you, okay, tree. I said tree, but that doesn't really look like trees we've drawn so far. So it's just a different way. So, this is just another way of drawing a tree. And I'm not specifying the root. So it's not a rooted tree. So that's what makes it a little weird, a little different from what we've seen so far. There's no designated root. But it connects everything and it doesn't have any cycles. So that's enough, it turns out. Okay. So I'm going to have you do an exercise real quick where you complete this algorithm in code to create a spanning tree. So I'm going to give you a random order of some edges, and you're going to use union find. And you're only going to add an edge if it doesn't form a cycle, otherwise you'll skip it. Okay, so it's not too bad once you got all the data structures in place. So go ahead and do that, and we'll keep talking.